Somewhere beyond the quiet rust of Mars, an interstellar visitor slipped past, silent, brilliant, and strangely incomplete. China's Tianwen-1 caught it. 3I-ATLAS, blazing with a bright core and wide coma, but missing the one feature every sun-kissing comet should have: a tail. China released the footage as breaking news, the first glimpse from Mars itself. But NASA's crystal-sharp high-rise images from the same window, still unseen, buried beneath the timing of a government shutdown. All we're left with are China and ESA's Space Invader pixels, while the clearest vantage sits locked away. So the question lingers: why does our best view of a cosmic stranger look like a glitch? And what's hiding in the frames we're not allowed to see? Settle in and stay through the end, because this mystery only gets stranger. Maybe the blur isn't the mystery at all. Maybe it's the silence around it. Because when a visitor from the stars breaks every rule, and its sharpest images never reach the public, we're forced to wonder, are we being protected from the truth, or shielded from something that could end us? If this mystery continues to have you hooked the way it has me, make sure to hit like and subscribe so you don't miss a single update as this unfolds in real time. Drop a comment with where you're tuning in from, what time it is there, and whether you believe we're getting the full truth about this interstellar intruder. And if you want to help this community grow, share this video on X, Facebook, Reddit, or even just in your group chats. You're the reason we can keep chasing stories like this, so thank you for having our back. Part 1. The Marside Reveal. Picture this for a moment. Right now, as you're listening to these words, there's a spacecraft silently circling Mars. It wasn't looking for ancient rivers or dusty canyons. Instead, its camera was pointed outward into the void, tracking something that shouldn't exist in our neighbourhood. Something from another star system entirely, and what it captured might change everything we thought we understood about visitors from beyond. The China National Space Administration just released imagery from their Tianwen-1 Mars orbiter, and the internet exploded. Not because of another crater or mineral discovery. No, this was different. The spacecraft had photographed 3I-ATLAS, an interstellar object, as it swept past Mars at roughly 29 million kilometres away. Think about that distance for a second. Nearly 30 million kilometres. That's about 77 times farther than the Moon is from Earth. And yet they captured it. But here's where things get interesting, maybe even unsettling. This marks the first time humanity has publicly seen an interstellar visitor from a Mars-side perspective. The first time ever. We've watched comets from Earth for thousands of years. We've sent spacecraft to rendezvous with them. But never before have we observed an object from beyond our solar system through the lens of another planet's orbit. That fact alone should give you chills. It's a fundamental shift in how we witness the cosmos. We're no longer bound to one vantage point. We're becoming multiplanetary observers, whether we realize it or not. Now, the State Council of China made sure everyone knew about this achievement. They framed it as breaking news, emphasizing that this was the only Mars-side data available to the public at that moment, and they weren't wrong. While NASA's Mars Reconnaissance Orbiter, equipped with a phenomenally powerful high-rise camera, also captured frames of 3I-ATLAS during the same window, those images remain locked away, unreleased. The official explanation mentions a US government shutdown delaying the data release, which sounds bureaucratic enough to be true. But the timing creates an uncomfortable vacuum. One nation shows the world what they found, while another nation's potentially superior images sit in digital darkness. What exactly did the Chinese imagery reveal? The frames show a bright, concentrated core surrounded by an enormous coma, the fuzzy cloud of gas and dust that envelops a comet's nucleus. This coma stretches thousands of kilometres across space, glowing faintly against the black. So far, that matches expectations. A comet near the Sun should develop a coma. Heat from our star causes the frozen volatiles, things like water ice, carbon dioxide and ammonia, to sublimate directly from solid to gas. This outgassing creates the signature halo we associate with comets. But here's the problem. There's no tail. None. At least not in any of the publicly released imagery, including these new Mars-side views. And that's where your brain should start asking uncomfortable questions. When a comet approaches the Sun and heats up, it doesn't just create a coma. The solar wind, that constant stream of charged particles flowing outward from our star, pushes the gas and dust away from the comet. radiation pressure acts like an invisible hand, sweeping the material into two distinct tails. One made of ionized gas, glowing blue and pointing directly away from the sun. Another made of dust, curving slightly as particles follow their own trajectories. Together, these tails can stretch millions of kilometers behind the comet, creating those spectacular sweeping arcs we see in photographs. So why doesn't 3I-ATLAS have one? Or does it, and we just can't see it? That's the mystery at the core of this story. Is the tail genuinely absent, or are we simply looking at it wrong? Maybe the imaging equipment isn't sensitive enough. Maybe the geometry is all wrong, and the tail is pointing directly toward or away from the camera, rendering it invisible. Maybe the dust particles are too large to be swept into a visible stream. Or maybe, just maybe, this object isn't behaving like a normal comet at all. Let me give you the stakes here, because they're higher than you might think. 3I-ATLAS is only the third confirmed interstellar object ever detected in our solar system. The third. After Oumuamua in 2017, which looked like nothing we'd ever seen and sparked endless debate about its nature, and 2I Borisov in 2019, which at least had the decency to look like a proper comet with a tail and everything. Now we have 3I-ATLAS, and it's refusing to play by the rules. It has a coma but no visible tail. It's from another star system but seems to be missing a fundamental feature, and the only public imagery comes from one nation's Mars orbiter, while potentially better data remains hidden. This isn't just about pretty pictures from space. This is about narrative control, about who gets to define what we know about the universe. When only one dataset exists in the public domain, that dataset becomes truth by default, whether it's complete or not. And right now, we're operating on incomplete information. We have dots and fuzzy images when we should have high-resolution frames capable of resolving fine structure. We have speculation when we should have data. We have questions multiplying faster than answers, so let me lay out where we're headed together. By the time we finish, you're going to understand what these images actually show and what they conspicuously don't show. You're going to grasp why missing data matters as much as the data we have, maybe more. We'll dig into the science of cometary tails, why they form, and what it means when they don't. We'll explore the broader implications for international space cooperation, or the lack thereof. And we'll widen out to other space. Developments in 2025 that you probably missed but shouldn't have. This is a speculative investigation, a what-if journey through the strange case of a visitor from the stars. What if the Mars-side imagery reveals something unprecedented? What if the missing tail tells us more than a visible one would? And what if the politics behind the data release matter more than the science itself? By the end, you might not have all the answers, but you'll definitely know which questions to ask. And in a universe this strange, that might be more valuable than certainty. Part 2. A closer look at the data. The high-resolution imaging camera on Tianwen-1, known as HIRIC, captured 3I-ATLAS between October 1st and 4th of 2025. The spacecraft was positioned in its orbit around Mars, roughly 30 million kilometers from the interstellar visitor. To put that in perspective, imagine standing in Los Angeles and trying to photograph a basketball in New York City. Now multiply that difficulty by several orders of magnitude and place both objects in the vacuum of space with no atmosphere to scatter light. That's approximately the challenge the Chinese team faced. What emerged from those observations was both expected and deeply puzzling. The images reveal a bright, intensely concentrated nucleus at the centre, exactly what you'd anticipate from a comet's solid core. Surrounding this nucleus blooms an enormous coma, that diffuse cloud of sublimated gas and entrained dust particles. According to the release, this coma extends thousands of kilometers in all directions, creating a fuzzy halo around the bright central point. So far, everything checks out. This is Comets 101. You have a frozen chunk of primordial material, the sun heats it. Volatiles boil off. A coma forms. Simple physics, reproducible, well understood. Except we're missing the final act of this performance. When a comet approaches the sun, the story doesn't end with coma formation. The solar wind, travelling at speeds of roughly 400 kilometers per second, slams into the expanding gas cloud. This wind is composed of charged particles, mainly electrons and protons, streaming outward from our star's corona. As these particles interact with the comet's gas, they ionize it, stripping electrons and creating a glowing plasma. This ionized gas responds to the sun's magnetic field, embedded in the solar wind, getting swept into a tail that points directly away from the sun. Meanwhile, dust particles released from the nucleus experience radiation pressure, the physical force exerted by sunlight itself. These particles, especially the smaller ones measured in micrometers, get pushed outward, forming a second tail that curves gently as the particles follow their own orbital trajectories. That's the classic model. That's what we see with nearly every comet that ventures into the inner solar system. Hale-Bopp in 1997 displayed spectacular dual tails visible to the naked eye. Comet Neowise in 2020 created similar structures captured by millions of amateur photographers. Even 2I Borisov, the previous interstellar visitor, showed a proper tail when it passed through in 2019. The physics is robust, the observations are consistent, the predictions are reliable. So why is 3I-ATLAS breaking this pattern? In every publicly released frame, including the new Mars-side imagery, the tail is conspicuously absent. You see the nucleus, you see the coma. But where the tail should extend, stretching potentially millions of kilometers into space, there's nothing but darkness, just the background stars and the void. Now, before we tumble down the rabbit hole of wild explanations, we need to consider the technical limitations of what we're actually looking at. The HIRIC camera wasn't designed for this kind of observation. It was built to image the Martian surface, to resolve geological features like impact craters, layered deposits, and potential landing sites. Its optics, its sensor sensitivity, its exposure times, all optimized for sunlit planetary surfaces relatively close to the spacecraft. Pointing this instrument at a faint, distant object in deep space is like using a microscope to watch birds. It might work, but you're operating outside the equipment's intended parameters. The camera's aperture measures approximately 38.7 centimeters across. That's respectable for planetary imaging, but relatively modest for deep space astrophotography. Contrast this with dedicated sky survey telescopes on Earth, which often sport mirrors exceeding a meter in diameter, or space telescopes like Hubble, with its 2.4-meter primary mirror. Collecting area matters when you're trying to gather photons from faint objects. The larger the aperture, the more light you capture, and the fainter the objects you can detect. HIRIC is working with less collecting power than ideal for this task. Then there's the geometry to consider. The spacecraft orbits Mars in a specific plane with a particular inclination. When it pointed at 3I-ATLAS, the viewing angle depended entirely on where both objects happened to be in their respective orbits. The phase angle, that's the angle between the Sun, the object being observed, and the observer, dramatically affects what you can see. If you're looking at a comet with the Sun behind you, you see it fully illuminated and any tail would be visible extending away. But if the geometry is different, if the Sun is to the side or partially behind the object, the illumination changes. Shadows appear. Features become harder to distinguish. A tail pointing away from the Sun might point roughly toward or away from your camera, appearing foreshortened or invisible. Stray light presents another challenge. Even though Tianwen-1 orbits above Mars's atmosphere, the planet itself reflects enormous amounts of sunlight. Mars is right there, a massive glowing sphere in the field of view. Preventing scattered light from Mars, or from the Sun itself, from contaminating your images requires careful baffling, precise pointing, and ideal timing. Any stray photons hitting the sensor wash out faint features, reducing contrast and making subtle structures like a tenuous tail impossible to detect. The Chinese statement accompanying the release mentioned that 3I-ATLAS appeared 10,000 to 100,000 times darker than typical Martian surface targets. 10,000 to 100,000 times darker. That's the difference between photographing a sunlit desert and trying to capture a shadow in a cave. The exposure times required to gather enough signal from such a faint object create their own problems. The spacecraft is moving, the object is moving. Even with careful tracking, motion blur becomes inevitable, and if you expose too long, you risk saturating the sensor on the bright nucleus while still failing to capture the faint tail. So maybe the tail is there. Maybe it's just too faint for HIRIC to detect given the exposure times, the collecting area, and the geometry. Maybe it's pointing in an unfavourable direction, aligned with our line of sight so it appears compressed into invisibility. Maybe the dust particles are larger than normal, measured in millimeters rather than micrometers, and they don't respond to radiation pressure the same way. Larger particles have more mass relative to their surface area, so the force of sunlight pushing on them becomes negligible compared to their inertia. they'd fall back toward the comet or drift away in random directions rather than forming a coherent tail. Or maybe, and this is where things get genuinely strange, maybe the object genuinely lacks a tail. Maybe something about its composition, its thermal history, its age or its origin makes it fundamentally different from the comets we're used to studying. Maybe being an interstellar traveller, spending millions or billions of years exposed to cosmic rays and interstellar radiation, changes how these objects behave when they finally encounter a star again. But we can't know which explanation is correct based solely on coarse imagery from one camera. We need more data. We need different viewing angles. We need spectroscopy, photometry, long-term monitoring. We need, quite frankly, the high-res images that are supposedly sitting on a hard drive somewhere at NASA, waiting for a government shutdown to end and a bureaucratic process to complete. Because right now, we're trying to solve a cosmic mystery with one hand tied behind our backs, and that should bother anyone who cares about actually understanding what's happening in our solar system. Part 3, the high-res absence and the data gap. The Mars Reconnaissance Orbiter has been circling the red planet since March of 2006. For nearly 20 years, it's functioned as our premier eyes above Mars, equipped with instruments capable of resolving features as small as a dinner table from orbit. The crown jewel of this spacecraft is HiRISE, the high-resolution imaging science experiment, a camera so powerful it can distinguish individual boulders on the Martian surface and track the seasonal appearance of dark streaks that might indicate flowing water. When engineers designed HiRISE, they created what remains the most capable optical telescope ever sent to another planet. Its primary mirror stretches 50 centimetres across, significantly larger than HIRIC's 38.7 centimetres. That extra collecting area translates directly into sensitivity, resolution, and the ability to detect faint features against dark backgrounds. So when 3I-ATLAS swept past Mars in early October of 2025, NASA pointed MRO's instruments at the visitor. The spacecraft captured frames. The data downloaded to Earth. Scientists presumably analysed what they received. And then, nothing. No public release, no press conference, no imagery shared with the astronomical community or the general public. The frames exist somewhere in NASA's vast data archives, but they remain inaccessible to the very people who funded the mission through their tax dollars. The explanation provided centres on a US government shutdown. These shutdowns occur when Congress fails to pass appropriations bills, forcing federal agencies to cease non-essential operations until funding resumes. During these periods, NASA's public communications often go dark. Websites stop updating, press releases pause, data processing teams get furloughed. It's bureaucratic gridlock with cosmic consequences. But here's the uncomfortable question nobody seems willing to ask directly. Why would a government shutdown prevent the release of already captured imagery? The data exists, the download happened, the files are there. Putting them on a public server and issuing a press release requires minimal resources. We're not talking about launching a new mission or operating a rover. We're talking about sharing photographs. Meanwhile, lawmakers have apparently urged NASA to release the HiRISE frames, according to reports. Members of Congress want to see what American spacecraft observed, which suggests the delay isn't just routine bureaucracy. There's pressure being applied, questions being raised, an awareness that this situation looks bad from a public perception standpoint. When China releases their Mars-side imagery first and frames it as breaking news, and American data that could potentially provide superior resolution remains hidden, it feeds a narrative. That narrative goes something like this. China is open, transparent, sharing their discoveries immediately. America is closed, secretive, holding back information for unknown reasons. Now, let's be precise about what this gap actually means. If HiRISE captured 3I-ATLAS with its full capabilities, those images would resolve details impossible to see in the HiRIC frames. We're talking about potential dust jets erupting from the nucleus, evidence of fragmentation or structural changes, the faint outer edges of the coma where it transitions to background space, and critically, any indication of a tail, no matter how tenuous. These structures might appear as subtle brightness gradients, barely distinguishable from noise but detectable with proper processing. The HiRISE team has decades of experience squeezing every photon of information from their data. They know how to enhance faint features, how to stack multiple exposures, how to subtract background stars and cosmic rays. If a tail exists, they'd find it. But we don't get to see that analysis. We don't get to examine the evidence ourselves or read the team's interpretation. Instead, we're left with the Chinese data as the sole publicly available Mars-side perspective, which gives it outsized influence on how this story gets told. In science, replication matters. Independent verification matters. When only one dataset exists in the public domain, you can't cross-check results, identify instrument artifacts, or build confidence through convergent observations. You just have to trust that the available data represents the complete picture. This situation highlights a crucial distinction that often gets blurred in space exploration. There's a difference between first discovered, first analysed, and first released. First discovered would mean the moment photons from 3I-ATLAS hit the detector, creating the initial electronic signal. That probably happened nearly simultaneously for both HIRIC and HiRISE, give or take hours based on their respective orbits and pointing opportunities. First analysed means when scientists extracted meaningful information from the raw data, processed the images, measured the coma size, searched for a tail, and drew preliminary conclusions. That analysis likely occurred within days for both teams. But first released, that's when the public learns what was found, and in this case China won that race by default. Does it matter? You might argue that scientific priority should go to whoever publishes peer-reviewed results first, not whoever issues a press release quickest. That's the traditional academic standard. The paper in Nature or the Astrophysical Journal carries more weight than a government press conference. But we don't live in a purely academic world anymore. We live in an era of instant information, social media amplification, and public engagement with science happening in real time. When millions of people learn about a discovery through news articles and social media posts, that shapes the narrative permanently. The peer-reviewed paper, when it eventually appears months or years later, rarely receives the same attention. There's also a perception issue that transcends the science itself. Space exploration has become a venue for demonstrating technological prowess and national prestige. The space race of the 1960s wasn't just about reaching the moon. It was about proving which political system could achieve the impossible. That dynamic never really disappeared, it just evolved. Today, China lands rovers on the far side of the moon, builds a space station, and announces plans for crewed Mars missions. The United States maintains the International Space Station, flies the most advanced rovers on Mars, and operates the James Webb Space Telescope. Europe contributes sophisticated instruments and collaborative missions. Private companies like SpaceX disrupt traditional models. Everyone watches everyone else, comparing achievements, measuring capabilities, and jockeying for leadership. In this context, being first to release Mars-side imagery of an interstellar object matters symbolically. It says something about transparency, efficiency, and willingness to engage the public. Fair or not, accurate or not, the narrative becomes, China showed us what they found immediately, while America sat on the data. And narratives, once established, prove remarkably resistant to correction. Even if NASA eventually releases stunning high-rise images that reveal unprecedented detail, the story will still mention how China released first during an American government shutdown. That qualifier becomes permanent. Here's where speculation becomes irresistible, even if unsupported by evidence. What if the high-rise frames show something unexpected? What if they captured clear evidence of a tail that contradicts the Chinese imagery? What if they reveal fragmentation, jets, or structural anomalies that raise uncomfortable questions about what this object actually is? Would that create pressure to delay release until a thorough analysis could rule out instrument artifacts or processing errors? I'm not suggesting a conspiracy or a cover-up. I'm simply noting that when data remains hidden, while other data becomes public, human nature fills the gap with possibilities. We wonder what's being withheld and why. The frustrating reality is that we may never know the behind-the-scenes reasoning. Government shutdowns are real, budget pressures are real, staff furloughs are real, processing pipelines have genuine technical requirements that can't be rushed without risking errors. But none of that changes how this looks from the outside, or the fact that right now, at this moment, we're trying to understand an interstellar visitor using incomplete information, while potentially superior data sits in digital limbo. Part 4. The Missing Tail and What That Means. Let's confront the central mystery directly. Where is the tail? When a comet ventures into the inner solar system approaching the Sun, we expect certain behaviours as reliably as we expect water to freeze at 0 degrees Celsius. The Sun's radiation heats the nucleus. Frozen volatiles sublimate, transitioning directly from solid to gas without passing through a liquid phase. This outgassing creates pressure, forcing material to escape the weak gravitational field of the comet's small nucleus. Gas molecules carry dust particles with them, creating the coma. So far, 3I-ATLAS follows the script perfectly. But then the solar wind should take over, sweeping that material into distinct tails, and that's where our visitor goes off script. The solar wind consists of charged particles, primarily electrons and protons, streaming outward from the Sun at hundreds of kilometers per second. This isn't a gentle breeze, it's a supersonic plasma flow powerful enough to create Earth's magnetosphere, compress it on the day side and stretch it into a long tail on the night side. When this wind encounters the neutral gas molecules in a comet's coma, the particles ionize them through collisions and electromagnetic interactions. Once ionized, the gas becomes sensitive to magnetic fields embedded in the solar wind. These fields effectively grab the ionized material and drag it away from the comet, creating the characteristic blue ion tail that points directly away from the Sun regardless of the comet's direction of travel. Simultaneously, dust particles experience radiation pressure. Photons from the Sun carry momentum, and when they reflect off or are absorbed by dust grains, they transfer that momentum to the particles. For small grains, measured in micrometers, this force can be significant relative to the particle's mass. The pressure literally pushes the dust away from the nucleus, creating a curved dust tail. The curvature occurs because the dust particles continue orbiting the Sun even as they're being pushed, so their trajectory represents a combination of their orbital motion and the outward push from radiation pressure. Larger particles respond less to radiation pressure because they have more mass per unit surface area, so they don't get swept as far, and may fall back toward the comet. This is textbook physics. We can calculate the expected tail length, brightness, and morphology based on the comet's distance from the Sun, its outgassing rate, the dust-to-gas ratio, and the solar wind conditions. For a comet like 3I-ATLAS, which passed relatively close to the Sun, we should see substantial tail development. The fact that we don't demands an explanation, and there are several possibilities worth examining. First, consider observational geometry. If the tail happens to point directly toward or away from our viewing angle, it would appear foreshortened, potentially compressed to the point of invisibility. Imagine looking down the length of a rope versus seeing it from the side. From the side, the rope's full length is apparent. From the end, you just see a dot. If the geometry aligned such that the tail extended along our line of sight, we might miss it entirely despite it being physically present. The Mars-side observations don't automatically solve this problem. They provide a different vantage point, yes, but that vantage could still align poorly with the tail's orientation. We'd need observations from multiple directions, preferably perpendicular to each other, to rule out geometric effects conclusively. Second, instrument sensitivity remains a limiting factor. Both HIRIC and potentially HiRISE were imaging an extremely faint object at enormous distances. If the tail exists but radiates at surface brightness levels below the detection threshold of these instruments, it simply wouldn't appear in the images. This isn't a failure of the cameras or the missions, it's just physics. Every detector has a noise floor, a minimum signal level required to distinguish real photons from random electronic fluctuations. Push below that threshold and you see nothing but noise. Longer exposures help, but they introduce motion blur and other complications. There's a practical limit to what you can detect from a spacecraft not specifically designed for deep space astrophotography. Third, consider composition. The James Webb Space Telescope observed 3I-ATLAS spectroscopically, analysing the light from its coma to determine chemical composition. The results proved surprising. The carbon dioxide to water ratio measured approximately 8:1, meaning for every molecule of water detected, there were 8 molecules of carbon dioxide. That's extremely unusual. Most comets show water as the dominant volatile, with carbon dioxide playing a supporting role. But 3I-ATLAS flips that relationship. Why does this matter for the tail? If the nucleus contains abundant carbon dioxide but relatively little water, and if the dust is somehow bound more tightly, or composed of larger particles, you could end up with vigorous outgassing that creates a large coma but doesn't produce much visible dust tail. The gas tail might still form, but if it's composed primarily of carbon dioxide ions rather than water ions, its brightness and visibility could differ from typical comets. Carbon dioxide sublimate at lower temperatures than water ice, so it activates farther from the Sun. By the time 3I-ATLAS reached perihelion, maybe it had already exhausted its easily accessible carbon dioxide, reducing outgassing rates and tail production. Fourth, the possibility of large dust grains deserves serious consideration. If the nucleus sheds predominantly millimetre-sized or larger particles instead of the usual micrometre-sized grains, those particles wouldn't respond effectively to radiation pressure. They'd have too much mass relative to their surface area. Instead of being swept into a tail, they'd follow ballistic trajectories, falling back to the nucleus or drifting away slowly in unpredictable directions. You'd get a coma from the gas and these larger particles, but no coherent dust tail structure. The absence of a tail would then indicate something fundamental about the object's composition and fragmentation, behaviour rather than being a geometric or instrumental artefact. Fifth, consider evolutionary age and activity cycles. Perhaps 3I-ATLAS is an old, depleted comet that lost most of its volatile inventory during previous encounters with stars before entering our solar system. If the surface became coated with a refractory lag deposit, a crust of non-volatile material left behind as ices sublimate, then activity would be suppressed. You might see some outgassing from cracks or fresh exposures, enough to create a coma but not the vigorous sustained activity needed for tail formation. The object would look like a dying comet, exhausted and fading, approaching the end of its active lifetime. The final possibility, and the one that generates the most controversy, is that 3I-ATLAS isn't a typical comet at all. Being interstellar changes everything. This object formed around a different star, in a protoplanetary disk with potentially different chemical abundances, temperature gradients, and formation conditions. It spent millions or billions of years travelling through the interstellar medium, exposed to cosmic rays, collisions with gas and dust, and radiation environments we can barely imagine. That journey could have altered its structure, composition, and behaviour in ways we don't fully understand. Maybe interstellar objects simply don't behave like solar system comets. Maybe the assumptions we've built from studying our own system's comets don't apply to visitors from elsewhere. Some voices, including physicist Avi Loeb, have even raised the possibility of artificial origin. If the object displayed anomalous acceleration, unusual spectral properties, or geometric regularity, such speculation might gain traction. But based on current observations, there's no compelling evidence for anything other than a natural celestial body. The absence of a tail, while puzzling, doesn't constitute proof of artificial construction. It's an anomaly requiring explanation, not a smoking gun for extraterrestrial technology. Science demands extraordinary evidence for extraordinary claims, and so far we don't have that evidence. What we have is an interstellar comet that refuses to behave normally, and that should be intriguing enough without invoking aliens. The implications extend beyond this single object. If we've misunderstood something fundamental about tail formation, dust grain dynamics, or cometary composition, then our models need revision. If interstellar objects behave differently from solar system comets due to their origins and histories, then we need to develop new frameworks for understanding them. And if geometric or instrumental effects explain the missing tail, then we need better observational strategies, multiple vantages, and more sensitive instruments to avoid similar confusion in the future. Right now, we're flying somewhat blind, making educated guesses based on incomplete data, while the key missing piece, those high-rise images, remains frustratingly out of reach. That's where we stand, staring at an interstellar visitor that simultaneously confirms our basic understanding of cometary physics and violates our specific predictions about how tails should appear. Part 5. Why it matters. Beyond the pretty pictures, you might reasonably ask why any of this matters. An interstellar object passed through our solar system. Spacecraft photographed it from Mars. The images show a coma but no tail. Science will eventually figure out the explanation. Papers will be published, and life will go on. Why dedicate thousands of words and considerable mental energy to a cosmic curiosity that doesn't directly affect anyone's daily existence? The answer operates on multiple levels, each expanding the significance far beyond a single confusing photograph. First, Consider what 3I-ATLAS represents fundamentally. This is material from another star system. The atoms in that nucleus, the molecules in that coma, they didn't form from our Sun's protoplanetary disk 4.6 billion years ago. They condensed around a different star, possibly earlier in the galaxy's history, possibly in a region with different chemical abundances. Studying this object gives us a window into stellar formation processes beyond our immediate neighbourhood. We can compare its composition to solar system comets and ask, are they similar or different? If similar, does that suggest universal processes operating the same way everywhere? If different, what does that tell us about the diversity of planetary systems and the materials available for building planets? The spectroscopic data showing a carbon dioxide-dominated coma already hints at something interesting. That extreme ratio might indicate formation in a particularly cold region, perhaps beyond the carbon dioxide ice line in the parent protoplanetary disk. Or it could suggest the object came from a system with unusual chemical abundances, maybe a star with different metallicity than our Sun. Each piece of information constrains the possible histories, narrows the range of formation scenarios, and helps us understand not just 3I-ATLAS, but the broader population of interstellar objects that must exist throughout the galaxy. We've now confirmed 3 such visitors in less than a decade. How many more are passing through undetected? What can they teach us about the processes that build solar systems and create the conditions for life? Second, the Mars-side vantage itself represents a paradigm shift. For all of human history until approximately 2025, our observations of celestial objects came from one location, Earth's surface or Earth's orbit. We could only see the universe from our planet's perspective. That's changing rapidly. We now have spacecraft orbiting Mars, Saturn and Jupiter. We have probes in the outer solar system and beyond. Each of these platforms represents a potential observatory, a new angle from which to view cosmic phenomena. The Tianwen-1 observations of 3I-ATLAS demonstrate the practical value of this multi-vantage approach. Different viewing geometries reveal different features. An object invisible from one angle becomes obvious from another. As our spacecraft network expands, we'll increasingly be able to coordinate observations, triangulate positions, measure parallax, and build 3-dimensional models of transient events. Imagine a future where a new interstellar object is detected by Earth-based surveys. Within hours, we repoint Mars orbiters, Jupiter spacecraft, and outer solar system probes to capture the visitor from multiple directions simultaneously. We coordinate exposure times, filter selections, and pointing strategies to maximize scientific return. The resulting dataset would be immeasurably richer than what we're currently wrestling with for 3I-ATLAS. But getting there requires missions designed with dual purposes, primary objectives like Mars geology or planetary atmosphere studies, plus secondary capabilities for opportunistic deep space observations. The fact that Tianwen-1 successfully captured 3I-ATLAS proves the concept works. Third, and perhaps most uncomfortable, is the question of transparency and data sharing in modern space exploration. The Chinese release of their imagery, framed as breaking news and heavily promoted by state media, achieved several goals simultaneously. It demonstrated technical capability. We have spacecraft at Mars that can conduct challenging observations. It showcased openness. We're sharing our discoveries immediately with the world. And it created a narrative advantage. While others hold back data, we provide transparency. Whether these were explicit strategic goals or fortunate side effects of normal operations, the result remains the same. In the public's mind, China showed us what they found while American data stayed hidden. This matters because space exploration increasingly operates in a competitive geopolitical environment. The Cold War space race positioned space achievements as proxies for ideological superiority and technological might. The current environment feels similar but more complex, with multiple nations and private entities pursuing independent capabilities. China has explicitly framed space exploration as essential to national rejuvenation and technological leadership. The United States sees maintaining its traditional dominance as crucial for economic and security interests. Europe seeks independence from both while promoting international cooperation. Private companies pursue profit, access, and occasionally utopian visions of space settlement. These competing interests don't always align with the ideal of open science, where data gets shared freely and credit follows peer-reviewed publication rather than press releases. The question becomes, does this competitive dynamic accelerate progress or impede it? One could argue, that competition drives investment, innovation, and achievement. Without the space race, would we have reached the moon in 1969? Probably not. Competition creates urgency, justifies budgets, and motivates excellence. But competition also encourages secrecy, duplication of effort, and missed opportunities for collaboration. When datasets remain siloed, science suffers. When political considerations override scientific priorities, we make suboptimal decisions. The delayed release of high-rise imagery, whether due to government shutdown or other factors, represents exactly this kind of friction between national interests and scientific ideals. Think about it through a concrete analogy. Two mountaineering teams attempt to summit an unclimbed peak. Team A reaches the top first, but their camera malfunctions, so they only get blurry phone photos. Team B summits a day later with professional photography equipment, capturing stunning high-resolution panoramas. When Team A immediately publishes their blurry photos with a press release claiming first to summit, they establish the narrative. Even when Team B releases their superior images later, the story forever includes the phrase, Team A reached the summit first but only captured blurry images. That qualifier colours every subsequent discussion. Apply this to 3I-ATLAS, and you see the problem. China released first with HIRIX's limited resolution frames. When NASA eventually releases HIRIS's potentially superior images, the story will always mention that China beat them to publication during a government shutdown. That becomes part of the permanent record, regardless of image quality or scientific value. Now consider the missing tail in this context. If the high-rise images reveal a tail that the Chinese imagery missed, that would be scientifically significant but narratively awkward. It would suggest that the first Mars-side perspective was incomplete or misleading, even if unintentionally. Conversely, if high-rise confirms the absence of a tail with higher fidelity, that strengthens the mystery and validates the Chinese observations. Either way, we need that data to complete the picture. Operating with only one dataset in a matter, this unusual feels like trying to understand a crime scene where half the evidence remains locked in a vault. You can theorize all you want, but you're fundamentally constrained by what you can examine. The broader implication touches on data equity in publicly funded space science. If taxpayers in the United States funded the Mars Reconnaissance Orbiter through NASA's budget, do they have a right to timely access to the data it collects? Most would argue yes, within reasonable constraints for processing, validation, and scientific priority for the mission teams. But timely becomes subjective when bureaucratic delays intervene. Meanwhile, Chinese taxpayers funded Tianwen-1, and their space agency provided immediate public access to the results. This creates an asymmetry that shapes global perception of who practices open science and who doesn't. Fair or unfair, that perception has consequences for international collaboration, public trust, and the political support necessary to fund future missions. This single missing tail on an interstellar comet thus becomes a nexus where multiple issues converge. Scientific mystery meets instrumental limitations. Observational geometry intersects with mission capabilities. National space programs compete while needing to cooperate. Data transparency clashes with bureaucratic realities. And the public watches, trying to make sense of conflicting narratives and partial information. The pretty pictures from Mars represent something far larger than simple documentation of a celestial visitor. They represent choices about how we explore the cosmos, who controls the narrative of discovery, and whether our species can coordinate effectively enough to understand the universe we find ourselves in. Those aren't trivial questions, and the answers we develop through cases like this will shape space exploration for decades to come. Part 6. Instrumentation and Viewing Geometry Unpacked. Let's pull back the curtain on the technology and orbital mechanics that determine what we can actually see from Mars. Understanding why an image looks the way it does requires grasping the complex interplay between camera specifications, spacecraft positioning, target geometry, and the fundamental physics of light. It's easy to look at a photograph and assume it shows objective reality. In truth, every image represents a negotiation between what exists and what the instrument can capture under specific conditions. The Tianwen-1 mission arrived at Mars on February 10th of 2021, representing China's first successful Mars orbital mission. The orbiter carries multiple instruments, but the high-resolution imaging camera, HIRIX, serves as the primary optical imaging system. Engineering specifications indicate an aperture of approximately 38.7 centimeters, which determines how much light the telescope can gather. In astronomy and astrophotography, aperture functions as the fundamental limiting factor for sensitivity. A larger aperture collects more photons per unit time, allowing detection of fainter objects or shorter exposure times to freeze motion. Hyrix aperture is respectable for planetary surface imaging, where targets are large, close, and brightly illuminated by sunlight. But for observing a faint comet tens of millions of kilometers away, it represents a significant constraint. Compare this to NASA's Mars Reconnaissance Orbiter, which entered Mars orbit in March of 2006 and has been operating for nearly 2 decades. The high-rise camera aboard MRO features a larger primary mirror, over 50 centimeters in diameter. That additional collecting area translates to improved sensitivity for faint targets. More importantly, HiRISE was designed specifically for ultra-high-resolution imaging, with sophisticated detectors, precision optics, and extensive ground processing pipelines honed over years of operation. The team knows how to extract maximum information from their data, how to stack images, subtract backgrounds, and enhance subtle features. This institutional knowledge matters as much as the hardware. Both spacecraft orbit Mars in elliptical paths, swinging close during periapsis and reaching greater distances at apoapsis. Tianwen-1's orbit has an inclination that determines which latitudes it passes over during each revolution. When the team wanted to observe 3I-ATLAS, they had to wait until the spacecraft's position aligned favourably with the comet's position in space. You can't just point anywhere anytime. The spacecraft has attitude control limits, power constraints, data storage limitations, and competing priorities. Imaging a deep space target requires careful planning, precise pointing and timing that accounts for orbital mechanics, target motion, and visibility windows. Think about the viewing geometry as a 3-dimensional puzzle. The Sun occupies one position, 3I-ATLAS occupies another, and the spacecraft orbits Mars at a third location. The angle between the Sun and the target, as seen from the spacecraft, determines illumination. If the Sun is behind the observer, the target appears fully lit, like a full moon. If the Sun is to the side, you see partial illumination, like a crescent or quarter moon. If the Sun is behind the target, you're looking at the dark side with only scattered light visible. For 3I-ATLAS, the phase angle during the Tianwen-1 observations determined how much of the coma and potential tail would be illuminated from the spacecraft's perspective. Additionally, the background matters enormously. The spacecraft isn't photographing the comet against a blank canvas. It's imaging through a field containing stars, galaxies, cosmic rays hitting the detector, and scattered light from Mars itself. Even though Tianwen-1 orbits above the atmosphere, Mars remains a huge bright object nearby. Stray light management becomes critical. Baffles and optical design minimize scattered photons, but you can never eliminate them entirely. Any light contamination reduces contrast, making faint features harder to distinguish from noise. The Chinese statement noted that 3I-ATLAS appeared 10,000 to 100,000 times darker than typical Martian surface targets. Let that sink in for a moment. The instrument was designed to photograph sunlit rocks, sand dunes, and crater floors from orbit. Those surfaces reflect solar radiation efficiently, creating bright, high-contrast images. Now point that same camera at an object radiating or reflecting 1/10,000th to 100,000th as much light. The exposure times required to gather sufficient signal increase proportionally, but longer. Exposures create problems. The spacecraft is moving at several kilometers per second in orbit. The target is moving along its trajectory through the solar system. Even with tracking to compensate for motion, anything beyond a fraction of a second introduces blur. The coma's central condensation might stay sharp, but diffuse structures like a faint tail would smear into invisibility. Sensor saturation presents another challenge. The bright nucleus of 3I-ATLAS concentrates light into a small area on the detector. Push the exposure long enough to capture faint outer structures, and you risk saturating the pixels imaging the nucleus. Once saturated, those pixels provide no useful information and can bleed charge into adjacent pixels, creating artifacts. Balancing exposure to capture both bright core and faint extended features requires either sophisticated dynamic range techniques or multiple exposures at different settings combined during processing. Consider also the spectral sensitivity of the detector. Most spacecraft cameras use silicon-based CCDs or CMOS sensors optimized for visible wavelengths. These detectors respond strongly to red and near-infrared light, less so to blue and ultraviolet. If 3I-ATLAS's tail emitted primarily in wavelengths, where the detector is less sensitive, it would appear fainter than if it radiated across the full visible spectrum. The spectroscopy showing a carbon dioxide-dominated coma matters here, because CO2 ions emit characteristic wavelengths that might not match the detector's peak sensitivity. Now apply all these factors to the question of the missing tail. If the tail extends perpendicular to our line of sight, it should be visible as a structure extending from the coma. But if it points toward or away from the observer, it becomes foreshortened, compressed along the line of sight into a much smaller apparent length. Imagine a long corridor. Viewed from the side, you see its full extent. Viewed from one end, looking down its length, you see only the nearest opening. Geometric foreshortening can make a tail millions of kilometers long appear as a barely detectable brightening, or disappear entirely against the coma's brightness. The Mars side observation doesn't automatically solve this problem. It provides a different vantage point, true, but whether that vantage reveals the tail depends entirely on the relative geometry. If the tail happens to point in a direction poorly aligned with both Earth-based telescopes and Mars orbiters, we might miss it from multiple perspectives. Ideally, we'd have observations from directions separated by large angles, providing orthogonal views that eliminate geometric ambiguity. We don't have that yet, and the missing high-res data makes the situation worse by denying us a second Mars-based perspective with different instrument capabilities. Here's an analogy that might clarify the challenge. Imagine you're trying to photograph a firefly at night while standing next to a bonfire. The firefly produces faint light, but the bonfire floods your vision with brightness. Any light scattered from the bonfire into your camera overwhelms the faint signal from the firefly. Even if the firefly is there, even if it's glowing, you might not capture it given the overwhelming local illumination. Now imagine the firefly is also moving. Your camera was designed to photograph the bonfire's flames rather than distant insects, and you're not sure which direction to point. That captures some of the difficulty facing spacecraft trying to image faint comets from Mars orbit. None of this proves the tail is absent. It just explains why detecting a tail under these conditions represents a formidable technical challenge, and why the absence of a tail in the released imagery doesn't necessarily mean no tail exists. It might be there, hiding below the detection threshold, foreshortened by geometry, overwhelmed by the bright coma, or simply pointed in an unfavourable direction. But it might also be genuinely absent, which would tell us something profound about the object's composition and behaviour. Distinguishing between these possibilities requires better data, multiple vantages, longer observation periods, and sophisticated analysis techniques. Right now, we're working with limited information from one camera not optimised for this task, and drawing definitive conclusions under those constraints risks mistaking instrumental limitations for physical reality. Part 7. Composition and Activity. What we hypothesize. The chemistry of 3I-ATLAS might hold the key to understanding its strange behaviour, and fortunately we have more than just images to work with. The James Webb Space Telescope, that magnificent infrared observatory stationed at the Earth-Sun L2 Lagrange point, pointed its instruments at the interstellar visitor and captured spectroscopic data that reveals the chemical composition of the coma. What JWST found was surprising enough to merit serious attention from the planetary science community. Spectroscopy works by splitting light into its component wavelengths, like a prism creating a rainbow. Different molecules absorb and emit light at characteristic wavelengths determined by their quantum mechanical properties. Water molecules produce specific spectral lines. Carbon dioxide molecules produce different lines. By measuring which wavelengths appear enhanced or diminished in the comet's light, scientists can determine what gases are present in the coma and in what proportions. This technique has been refined over decades and provides remarkably precise compositional information. For 3I-ATLAS, the spectroscopy revealed a carbon dioxide to water ratio of approximately 8:1. That means for every molecule of water vapour detected in the coma, roughly 8 molecules of carbon dioxide were present. This is extraordinary. Most solar system comets show water as the dominant, volatile species, with carbon dioxide playing a secondary role. Typical ratios might be 1 part carbon dioxide to 10 or 20 parts water. 3I-ATLAS flips this relationship dramatically, showing the highest CO2 to H2O ratio ever observed among comets. What does this tell us? Several possibilities emerge, each with different implications for the object's origin and evolution. First, consider formation location. In a protoplanetary disk around a young star, different volatile species condense at different distances from the central star, creating distinct chemical zones. Water ice forms beyond the so-called snow line, where temperatures drop low enough for H2O to freeze. Carbon dioxide requires even colder temperatures, freezing beyond the CO2 ice line at greater distances. If 3I-ATLAS formed in the outer reaches of its parent system, beyond the carbon dioxide ice line but in a region depleted of water, you could naturally produce a CO2-rich composition. Alternatively, the thermal history might explain the anomaly. Imagine the nucleus as a layered structure, with different ices distributed at various depths. If the surface layers became heated and depleted of water ice during previous stellar encounters, or from internal radioactive heating, but deeper carbon dioxide-rich layers remained intact, then current outgassing might draw primarily from CO2 reservoirs. The water could be locked deeper in the nucleus, insulated by an outer crust of dust and refractory material. As the comet heats, carbon dioxide sublimates at lower temperatures than water, so you'd see CO2 outgassing first and most vigorously. Now connect this unusual composition to the missing tail problem. If the coma is gas-rich but dust-poor, you might not produce a prominent dust tail. Dust tails depend on having substantial quantities of small particles entrained in the outflowing gas. These particles get released as ices sublimate and the structure disintegrates. But if the nucleus is primarily CO2 ice with little dust content, or if the dust particles are unusually large and bound tightly, then you'd get vigorous gas outgassing, creating a large coma while producing minimal visible dust tail. The gas itself forms an ion tail when ionized by solar UV radiation and swept away by the solar wind. But ion tails are often fainter and require specific observational techniques to detect. Think about dust grain size distribution for a moment. When material in a comet nucleus breaks down, it fractures into particles spanning a huge range of sizes, from submicrometer dust grains to centimeter-sized chunks and larger fragments. The smallest particles, those measured in micrometers, respond strongly to radiation pressure because they have large surface area relative to their mass. Sunlight hitting these tiny grains imparts enough momentum to overcome their inertia, pushing them away from the nucleus and creating the classic dust tail. But larger particles, measured in millimeters or centimeters, have much more mass relative to their surface area. Radiation pressure becomes negligible compared to their inertia. These particles might get ejected from the nucleus by gas pressure, but then follow ballistic trajectories rather than being swept into a tail. They orbit the Sun independently, spreading along the comet's orbital path but not forming a coherent visible structure. If 3I-ATLAS sheds predominantly large dust grains rather than fine dust, you'd observe vigorous outgassing and a substantial coma from the gas and large particles, but no visible dust tail because the particles aren't responding to radiation pressure appropriately. This could result from the nucleus having undergone extensive processing during its interstellar journey. Cosmic rays, interstellar dust impacts, and radiation exposure over millions or billions of years could alter the surface structure, sintering dust grains together into larger aggregates or creating a hardened crust that fragments into chunks rather than fine powder. The photometric data from Earth-based observations adds another piece to the puzzle. The ATLAS survey network, which ironically shares its name with the comet, monitored the brightness and colour evolution of 3I-ATLAS as it moved through the inner solar system. These observations track how the cross-section of the coma changes with time, which relates to dust production rates. If you see the coma growing rapidly and brightening, that indicates increasing activity and dust production. If the coma remains relatively stable or shrinks, activity may be declining or already at low levels. For 3I-ATLAS, the photometric evolution shows changes that astronomers are still working to fully interpret. Colour measurements provide clues about dust grain properties, as different grain sizes and compositions scatter sunlight differently. Reddish colours might indicate organic-rich material or specific mineral compositions. Neutral or bluish colours could suggest different dust properties or gas-dominated scattering. The preliminary indications suggest behaviour somewhat atypical compared to well-studied solar system comets, but not so extreme as to defy explanation through conventional cometary physics. Here's where we venture into more speculative territory. What if 3I-ATLAS represents a hybrid object, something between a typical comet and a dormant asteroid? Some solar system bodies exist in this transitional category, showing weak cometary activity despite having largely asteroidal compositions. These objects may have lost most of their volatiles over millions of years of orbital evolution, leaving behind a mostly rocky core with residual pockets of ice. When they approach the Sun, they might produce a small coma from the remaining ice, but lack the vigorous activity needed for tail formation. If 3I-ATLAS is similarly depleted after billions of years travelling through the galaxy, it could exhibit exactly the behaviour we're observing: a prominent coma from the remaining volatiles, particularly the more easily sublimated carbon dioxide, but insufficient dust production for a visible tail. Another intriguing possibility involves fragmentation. Comets sometimes break apart under thermal and tidal stresses as they approach the Sun. If 3I-ATLAS fragmented before or during the observation period, shedding pieces of its nucleus that could alter its appearance dramatically. Fragmentation events often produce temporary brightening as fresh ice becomes exposed and sublimates rapidly, but they can also disrupt dust production patterns and alter the expected tail development. If we're observing this object during or after a fragmentation event, the lack of a tail might reflect unusual activity states rather than stable compositional properties. The implications extend beyond just explaining one odd object. If interstellar comets systematically differ from solar system comets in composition, structure, or behaviour due to their different formation environments and evolutionary histories, we need to develop new models and frameworks for understanding them. The 3 confirmed interstellar visitors so far show remarkable diversity. Oumuamua looked like nothing we'd seen before, possibly a flat, elongated object with no visible coma or tail. 2I Borisov appeared fairly typical, showing expected cometary behaviour with a visible tail. Now 3I-ATLAS presents a third pattern: prominent coma, unusual composition, no visible tail. 3 objects, 3 different behaviours. That small sample already suggests the population of interstellar visitors might be far more diverse than the comets native to our solar system. Understanding that diversity requires more observations, better data, and probably a few lucky breaks when another visitor passes through at an opportune time with multiple spacecraft positioned to observe it. Until then, we're extrapolating from minimal information, building hypotheses that future discoveries will either confirm or overturn. That's the nature of frontier science. You work with what you have, you make educated guesses, and you stay ready to revise everything when better data arrives. Part 8. The perception gap. Data, agency, politics. Now we wade into murkier waters where science intersects with national pride, institutional priorities, and the messy reality of how information flows in the modern world. The story of 3I-ATLAS isn't just about the object itself. It's about who saw what when they chose to share it, and how those decisions shape the narrative that millions of people now accept as truth. Let's map the players and their actions. China's National Space Administration, through the Tianwen-1 mission, captured imagery of 3I-ATLAS and released it publicly with considerable fanfare. The announcement came through official channels, amplified by state media, framed as a significant achievement demonstrating Chinese technological prowess and scientific transparency. The subtext was clear. We have the capability to conduct sophisticated observations from Mars, and we're sharing the results immediately with the world. No delays, no bureaucracy, no classified restrictions, just open science for the benefit of humanity. The European Space Agency also pointed instruments at the interstellar visitor, but published only relatively coarse positional data, often described as appearing like simple dots or Space Invader-style pixels rather than resolved imagery. This might reflect instrumental limitations, data processing priorities, or simply different communication strategies. ESA often operates more conservatively regarding preliminary data releases, preferring to wait for thorough analysis before making announcements. There's nothing inherently wrong with that approach, but it does mean they contributed less to the immediate public narrative. Then there's NASA, with the Mars Reconnaissance Orbiter and its powerful high-rise camera, perfectly positioned to capture higher resolution imagery than either the Chinese or European observations. The spacecraft acquired the data. the files downloaded to Earth. Scientists presumably examined them, and then silence. No public release, no preliminary images, no press conference. The explanation involves a US government shutdown interrupting normal operations and delaying data processing and publication. Lawmakers reportedly urged NASA to release the frames, suggesting political awareness that the delay looked bad from a public relations standpoint. Think about how this sequence played out in media coverage and public perception. The first articles about Mars-side observations of 3I-ATLAS featured the Chinese imagery prominently. Headlines emphasized China's achievement, often with variations of "China releases first Mars-side images of interstellar comet" or "Chinese spacecraft captures rare visitor." The narrative solidified quickly. China did something significant and shared it openly. By the time NASA might eventually release their data, the story has already been told. Any subsequent releases become updates to an existing narrative rather than defining moments. This matters because first impressions are difficult to overcome. In science, the publication record is supposed to determine credit and priority. The peer-reviewed paper in a major journal carries weight. Press releases are ephemeral. But we don't live in a world where only scientists pay attention to space news. Millions of people follow space exploration through news sites, social media, and YouTube channels. For them, the press release and the accompanying imagery are the story. The peer-reviewed paper, when it appears months later, barely registers. So whoever controls the timing of public releases effectively controls the narrative, regardless of what the scientific record eventually shows. Consider the concept of data equity in publicly funded research. When tax dollars support a mission like the Mars Reconnaissance Orbiter, should the data it collects be considered a public good requiring rapid release? Most scientists would argue yes, within reasonable constraints. Mission teams need time to validate data, remove artifacts, and conduct initial analysis. Proprietary periods allow the scientists who built the instruments and designed the observations to publish papers before the data becomes freely available to competitors. These protections are considered fair and necessary to incentivize participation in expensive, complex missions. But there are limits. Data should become public eventually, usually within months to at most a year or two, depending on the mission's data policy. A government shutdown disrupting this timeline creates an awkward situation. The delay isn't driven by scientific necessity or reasonable proprietary protections. It's purely bureaucratic, the result of political dysfunction preventing government agencies from operating normally. From the public's perspective, this looks like politics interfering with science. It feels arbitrary and frustrating, especially when other nations are releasing their data without apparent obstacles. Fair or not, it reinforces a perception that American space exploration, despite its technical excellence, gets tangled in bureaucratic red tape that hinders timely communication and public engagement. The geopolitical dimension adds another layer of complexity. Space exploration has always carried symbolic weight beyond its scientific value. The Cold War space race positioned achievements like Sputnik and the Apollo moon landings as demonstrations of ideological superiority and technological might. Reaching space first, orbiting first, landing humans on another world first, these milestones resonated far beyond their immediate practical value. They proved that a nation possessed cutting-edge technology, organizational capability, and the resources to accomplish extraordinary tasks. That dynamic never really disappeared. It evolved and became more multipolar, but the fundamental logic remains. China explicitly frames its space program as essential to national rejuvenation and the Chinese dream of reclaiming historical greatness. Mars missions, lunar sample returns, and space station construction serve partly as scientific endeavours and partly as demonstrations of China's emergence as a technological superpower. When Chinese spacecraft achieve firsts or accomplish difficult tasks, state media amplifies these achievements domestically and internationally. It's soft power, enhancing China's prestige and influence without firing a shot. The United States still dominates many aspects of space exploration, but feels its historical supremacy eroding. NASA's budget, while substantial, has declined as a percentage of federal spending since the Apollo era. Private companies like SpaceX have disrupted traditional paradigms, demonstrating capabilities that challenge NASA's exclusive role. Meanwhile, China's space program advances steadily, achieving milestones that once seemed exclusively American. the first far-side lunar landing, the Tianwen-1 orbiter and rover arriving at Mars on the first attempt, a functional space station after the ISS partnership excluded China. Each achievement shifts the balance of prestige and raises questions about future leadership in space. Europe pursues a different strategy, positioning itself as a collaborative partner, enabling international cooperation while maintaining independent capabilities. ESA contributes instruments to NASA missions, collaborates with China on lunar exploration, and builds sophisticated spacecraft like the upcoming JUICE mission to Jupiter. But Europe's approach emphasizes partnership over competition, which sometimes means accepting secondary roles in exchange for maintained access and influence. Private companies add yet another dimension. SpaceX's reusable rockets have slashed launch costs and enabled ambitious projects like Starlink. Blue Origin, Virgin Galactic, and emerging players pursue their own visions. These companies operate according to market logic rather than national prestige, though their success still reflects favourably on their home nations. The interplay between national space agencies and private enterprise creates a complex ecosystem where motivations, priorities, and communication strategies vary wildly. Now map all this complexity onto the simple question: why haven't the high-rise images of 3I-ATLAS been released? The technical answer involves government shutdowns and data processing timelines, but the perception is that America held back while China shared openly. That perception, regardless of its accuracy or fairness, has consequences. It affects how people view the relative openness of different space programs. It influences which nations get credit for discoveries. It shapes public trust in institutions and their willingness to share information promptly. Here's an uncomfortable analogy. Imagine two research teams working on a cure for a disease. Team A announces preliminary results showing promise, generating headlines and public excitement. Team B has more comprehensive data but waits to complete their analysis and publish formally. By the time Team B's paper appears, the narrative is already established. Team A found the cure. Team B's contribution becomes a footnote or confirmation rather than a discovery. The scientific record might eventually show both teams contributed equally, but public memory retains the first announcement. Apply this to 3I-ATLAS, and you see the problem. Even if NASA's high-rise data ultimately proves more valuable scientifically, China already claimed the public narrative by releasing first. Should it work this way? Probably not if we care about accurate attribution and scientific rigour. But this is the world we live in, where communication timing matters as much as content quality, and where political constraints can delay releases long enough to cede narrative control. Understanding this reality doesn't require endorsing it, but ignoring it means missing a crucial dimension of how modern space exploration actually functions beyond the idealized version we might prefer. Part 9. Conspiracies, Fringe Theories, and Cautious Science. When science hands us an object that refuses to behave the way a comet should, and when snapshots from the highest resolution instrument remain out of public reach, our collective imagination does what it always does. It fills in the blanks. People whisper about strange forces guiding 3I-ATLAS, wonder aloud why a bright coma would show no visible tail, and replay China's fast-released Mars-side video like a riddle carved into cosmic static. I think the oddest part is not that questions are being asked, but that they are being asked by people who usually roll their eyes at anything too speculative. When a dataset goes missing, even level-headed minds begin twitching toward what-ifs. When the name Avi Loeb lands in the discussion, ears perk up. Loeb has been open to unorthodox possibilities for interstellar objects since Oumuamua. He encouraged scientists to consider artificial origin ideas, not as fact, but as one possibility among many. With 3I-ATLAS refusing to show a tail even as it warmed near the sun, the same style of speculation reappeared. The argument goes like this: if a visitor behaves in non-comet ways, maybe it is not a comet. Maybe it is something built, not born. Maybe it is a sail, not an icy rock. Maybe this strange brightening without a tail points toward manoeuvring rather than sublimation. Of course, maybe it is simply a new kind of ice behaving in a way we have not modelled well. Either way, uncertainty gives room for stories. When we list claims, we can map them to evidence quickly. Artificial origin, missing tail, unusual brightening, interstellar trajectory. But status remains speculative, with no direct evidence. Unusual material or comet behaviour, strong carbon dioxide coma with atypical tail absence. That is supported by early spectroscopy, but still leaves us guessing. Data cover-up by NASA. Delayed high-rise release from the Mars Reconnaissance Orbiter. The status is simply delay during a government shutdown, not evidence of suppression. One could place those claims into a neat little table. The claim, the evidence, and the caveats. Every cell would be a reminder that uncertainty is not a conspiracy, but it can certainly smell like one if you stand too close. When you hold a mystery with gloves, the brain invents reasons. Some imagine the United States hiding imagery to avoid panic or embarrassment. Others imagine China rushing their low-resolution release to take a victory lap, knowing the higher-quality American pictures might show something more provocative. The truth might be mundane. Bureaucracy is slow, and mission priorities do not always line up with public curiosity. But the optics are strange. China releases grainy dots quickly. Europe publishes similar dots. The United States holds its silence. In a world addicted to real-time information, silence feels louder than speech. When a comet is expected to grow a tail due to solar heating and does not, experts ask about dust grain size, outgassing chemistry, viewing geometry, and illumination angles. The answer can be surprisingly simple, like, the dust is too large to be pushed into a visible tail, or, our viewing geometry hides the tail behind the coma. Many weird things have happened in astronomy that turned out to be nothing more than awkward angles and tricky pixels. But people crave narratives, not footnotes. When online spaces pick up a story, it mutates. One person asks if 3I-ATLAS could be a probe. Another posts a quick AI-enhanced crop showing a tiny speck that looks slightly rectangular. Someone else claims they heard an anonymous NASA intern say the image was held back on purpose. Each retelling drifts further from reality. The meme mills do their work. Suddenly, what started as a quiet scientific puzzle becomes an alien tech thriller with Mars as the witness. When scientists respond, they do so with caution. They remind everyone that extraordinary claims require extraordinary evidence. They stress that a missing tail is a clue, not a revelation. They remind us that Oumuamua's odd behaviour did not prove intelligent origin, and neither does 3I-ATLAS. They warn that premature conclusions can trap us in fantasy rather than help us find truth. But the cautious tone is sometimes interpreted as politically safe rather than scientifically honest. We are a species that has always suspected we are being kept in the dark. When we look past the noise, we find that mainstream science is simply trying to understand a puzzle. A carbon dioxide-rich coma with no visible tail is odd, but not impossible. The bright core may be a fragment or a chunk of ice shedding gas unevenly. The absence of a tail might be more about geometry or particle size than about alien design. The high-rise delay might be nothing more than backlog. The simplest explanations remain the likeliest. When we exhale, we realise that speculation is not the enemy. It is a tool, as long as we label it correctly. It invites us to imagine multiple explanations, to ask better questions, to refine our models. 3I-ATLAS is a reminder that even with our technology, the cosmos can still hand us puzzles that feel like riddles. And if the most compelling answer turns out to be mundane, that is still progress. Science advances whether the universe is ordinary or astonishing. When we look ahead, curiosity pulls us toward what comes next. New vantage points, better instruments, and perhaps more visitors. The strange behaviour of 3I-ATLAS may not be the end of the mystery, but merely the beginning. The puzzle invites a bigger question about how we watch the sky, how Mars helps us, and what we do when the unknown comes knocking again. Part 10. Why the broader field of interstellar objects and Mars-side vantage is changing. When you consider that only 3 interstellar objects have ever been confirmed, you realise how young this field truly is. 1 Oumuamua, 2 Borisov, 3 3I-ATLAS. That is it. 3 messengers in all of recorded history observed close enough for us to scratch our heads. That means every arrival is like catching a guest walking through a locked door. It feels almost rude not to stare. Scientists know the sample size is tiny, so each visitor becomes a chance to redefine what an interstellar object might be. When we talk about interstellar visitors, we usually assume we will observe them from Earth. But 3I-ATLAS shows how Mars-side vantage is changing everything. China's Tianwen-1 orbiter captured the object at around 29 million kilometres from Mars. That is not close, but it offered a geometry we rarely get. A different angle, no atmospheric distortion, and a relatively quiet background. A spacecraft circling another world suddenly becomes a cosmic photographer in a new studio. For the first time, the public saw an interstellar visitor, not from Earth looking outward, but from Mars looking outward. When the European Space Agency and China released their images, they looked like tiny Space Invader dots. Not pretty, but historic. These images demonstrated that Mars orbiters can be reoriented or timeshared to catch fast visitors. The question became, could this become standard practice? Could Mars orbiters, or even Jupiter orbiters, be used as an early warning telescope network? If an object is coming through the inner solar system, maybe Earth should not always be the camera operator. Maybe Mars and beyond should be part of the surveillance ring. When you consider future surveys, the Vera C. Rubin Observatory, formerly LSST, looms large. It is designed to scan huge swathes of sky nightly, catching faint objects before they slip past us. When Rubin becomes fully operational, we may detect dozens of interstellar objects each decade. That means Mars-side imagery will not be a stunt, but a workflow. We might find visitors early, warn the planetary network, and swivel every available camera to get data. There is talk of using Jupiter-side missions to do the same. Imagine an interstellar visitor passing through and being imaged by observers at multiple worlds. When academics propose new mission concepts, they imagine spacecraft pre-positioned to intercept interstellar objects. Not just flybys, but rendezvous, sampling, even return missions. Nothing like that has been approved yet, but the logic is compelling. If you know from Rubin that an object is coming, and you have a probe already stationed along a likely trajectory, then interception becomes possible. 3I-ATLAS is not going to be intercepted, but it hints at a future where Mars orbiters serve as scouts. When we think about this shift, we realise how passive we used to be. We waited, we spotted, we waved goodbye. But 3I-ATLAS pushed NASA, China and Europe into an awkward dance. China shared first. NASA stayed quiet. Europe shared modest images. The world felt like it had just watched a relay where the baton dropped. The frustration triggered new conversations about transparency, urgency and coordination. If Mars can give us new angles, maybe we need a Mars-based protocol. When an interstellar visitor approaches, every orbital camera becomes part of a distributed telescope. When we outline the challenges, they are obvious. Coordination requires diplomacy. Redirecting an orbiter requires time and fuel. Instruments are not always pointed outward. The cadence of mission science is planned months ahead, and not every spacecraft is nimble enough to pivot. But the 3I-ATLAS event proves it can work in a pinch, even if only rough data emerges. The symbolic value is huge. Mars is not just a target of study, but a platform doing astronomy. When we connect back to 3I-ATLAS, we realise its greatest gift may not be answers about tails or material composition. Its greatest gift may be the blueprint it gives us. Mars can help us observe interstellar visitors. A network of off-Earth cameras could become standard. A protocol could be written. And one day, a dedicated mission could chase an object with intelligence, planning, and maybe instruments built to sample gas or dust. When we imagine Mars becoming an outer space observatory, it feels like science fiction. But the concept is simple. You put eyes wherever you can. Earth, Moon, Mars, Jupiter. You watch in stereo. If you see an odd rock cruising by, you catch it from multiple angles. This is not about national competition. It is about building a solar system-wide surveillance system for visitors that may carry information about distant star systems. When we transition to Act 3, we realise that 3I-ATLAS is more than a cosmic weirdo. It is a catalyst. It pushes us toward multi-vantage astronomy, early detection, AI discovery, orbital interception, geopolitical wrangling, and new science around comet physics. And the story's getting bigger, because now, as we step into the next chapter, we will explore how other forces, including AI and surprising discoveries on Mars, could transform our ability to understand objects like 3I-ATLAS and whatever comes next. Part 11. AI-driven discovery of new objects in space. When astronomers began drowning in data, AI stepped in like a quiet assistant with sharp eyes. These days, survey networks scan the sky each night, generating oceans of images. Buried in those frames are small points of light that move in suspicious ways. AI digs, through those pixels noticing faint, fast travellers that human eyes might miss. One of the reasons 3I-ATLAS was even noticed is because distributed survey networks have evolved into semi-autonomous watchers, filtering noise and flagging the improbable. When we think of AI in astronomy, it is not about robots making decisions alone. It is about pattern recognition. AI learns what a normal asteroid looks like, what a normal comet looks like, and what a false alarm looks like. When something strange appears, the algorithm raises its hand. Astronomers then scramble to gather more data. In 2025, several observatories reported refining their anomaly detection algorithms, moving from traditional rule-based filters to deep learners that can detect odd behaviour. That means the next interstellar visitor may be flagged faster than 3I-ATLAS ever was. When we talk about AI and faint objects, the ATLAS network itself becomes central. The ATLAS system was originally designed to find objects that might threaten Earth, but its constant sky coverage and fast imaging cadence make it ideal for spotting interstellar drifters. AI improves that capability, allowing the network to pick out faint moving specks with almost casual ease. A faint object that would have been overlooked in 2010 is now found before breakfast. When we connect this to 3I-ATLAS, we imagine a future where AI does not just detect the visitor, but also predicts its odd behaviour. If the system notices that sublimation signatures are weak, that tail formation is absent, and that brightening curves are strange, it could immediately alert mission planners. China pivoted quickly with Tianwen-1 because the object was already generating buzz. But imagine an AI that flags a weird comet at 3 times the distance and gives Mars orbiters weeks of preparation time. When we consider how AI learns, we realise it does not just memorise. It builds internal maps of what is normal and what is abnormal. Some groups are training AI on synthetic data to look for solar sail signatures, expecting that an object propelled by radiation pressure might show specific accelerations. If such a signature appeared, the algorithm could whisper, "This one is weird," and the world might turn its attention in seconds. The speculation is not that AI will confirm alien technology, but that AI will alert humans to investigate more closely. When we think of survey pipelines, we recognise that every new telescope adds more data than humans can handle. The Vera C. Rubin Observatory will scan the sky repeatedly, finding countless transient objects. Without AI, that information would bury us. With AI, faint interstellar visitors will be routinely flagged. That means more follow-up, more imaging, and possibly more Mars-side captures. 3I-ATLAS is not the last. It might be the first of many to be analysed by a multi-planet optical network guided by machine intelligence. When we picture the future, we imagine dispatching fast probes from multiple worlds. AI could track an object and determine whether a craft should adjust course. The ultimate dream would be an autonomous interstellar visitor interceptor that patrols near Mars or Jupiter. When something strange crosses its field, the craft could adjust trajectory, deploy sensors, and send back data. AI improves reaction time, allowing us to engage with these travellers rather than merely observe from afar. When we turn back to today, AI is already redrawing how we study the sky. It helps classify supernovae, track asteroids, and find exoplanets. Its fingerprints are everywhere. The 3I-ATLAS event shows that information flow matters. China's fast release beat NASA's silence. But in the future, AI could force the issue, alerting multiple agencies before anyone decides to withhold data. If AI posts the alert publicly through auto-publish pipelines, then no single nation controls the first look. When we ask what might come next, we see the seeds of something transformative. AI detection leads to faster view angles. Mars-side vantage leads to better geometry. Interception leads to sampling. Sampling leads to understanding. And understanding might reveal whether these visitors are chunks of exotic chemistry or messages from distant worlds. The fact that AI can spot subtleties that humans miss means that our scientific horizon just widened. When we take a breath, we see the open loop. AI changes how we find objects. Mars changes how we see them. But what about the place doing the watching? Mars itself is becoming more than a dusty neighbour, and its evolving discoveries unlock new possibilities about what instruments in Martian orbit could achieve. And that leads us naturally to the next surprise. Part 12. Unexpected Mars Discoveries. 2025 Update. When Tianwen-1 turned its eyes from Mars to 3I-ATLAS, it reminded us that Mars orbiters are not one-trick machines. They can reorient, refocus, and study things beyond their primary mission. This flexibility grew from years of Mars exploration, where engineers found ways to squeeze extra science out of old hardware. In 2025, scientists reported new hints of subsurface ice deposits in mid-latitude regions, using radar returns that surprised many. The ice seems purer than expected, almost like frozen pockets preserved far from the poles. When this discovery surfaced, researchers were reminded that Mars is not static. It changes, stores secrets, and occasionally reveals them. Subsurface ice is important, not just for science, but for future explorers. But it also tells us something about instrumentation. The radars and spectrometers that map the ice are the same kinds of instruments that, when pointed outward, can help analyze visitors like 3I-ATLAS. A tool that finds water beneath Martian soil can also detect gas signatures from an object, passing millions of kilometers away. When another report emerged about unusual trace minerals near old volcanic plains, people blinked. These minerals hinted at unexpected temperature histories, possibly indicating past hydrothermal activity. Suddenly, Mars looked more complex. The instruments discovered silica polymorphs that implied hot fluids, not just cold volcanism. Some speculated about ancient habitats, others focused on the chemistry. But all agreed that the rovers and orbiters have been quietly rewriting our assumptions. When we connect this to 3I-ATLAS, we begin to see a pattern. The hardware near Mars is strong, versatile, and hungry for tasks. If you can map ice under soil, you can help map a comet's coma. If you can spot minerals on a planet's surface, you can help measure reflected light curves from an interstellar visitor. It becomes clear that the frontier of interstellar object observation is not limited to Earth-based telescopes. Mars is stepping into the role of cosmic lookout. When new dust storm mapping arrived in early 2025, revealing faster storm propagation than expected, scientists were surprised. Mars storms are notorious, but these reports indicated unusual acceleration patterns. Some models had to be adjusted. These same storm models are valuable for understanding how Mars orbiters must time their external observations. If a storm interferes with power or pointing, Mars might miss its moment. But the dust storm data also illustrated how flexible observation campaigns have become. Engineers can now repoint or reschedule dynamically. When we consider mission design, we can imagine a future where Mars orbiters carry dual-purpose payloads. One sensor for geology, one for astrophysics. China's quick reaction to 3I-ATLAS hints that such pivoting is doable. And if Mars continues to reveal new ice and mineral stories, the incentive to keep powerful sensors in orbit grows. More sensors means more opportunities to study passing visitors. When we take this further, we imagine a network of orbiters at Mars, Jupiter, and perhaps Saturn, all capable of shifting attention outward. Mars discoveries matter not only for planetary science, but because the infrastructure used to make those discoveries doubles as a distant observatory. We are seeing the first hints of a multi-planet astronomical observatory, born from repurposed mission hardware. When we peer ahead, we see that Mars might become a forward operating base for interstellar observation. If humans or robots establish small bases there, telescopes on the surface could track incoming visitors with less atmospheric distortion than Earth. A dusty Martian sky is still clearer than Earth's atmosphere for much of the spectrum. Mars bases could store instruments, spare parts, and computing clusters. The line between planetary science and astronomy may blur. When we consider the philosophical shift, Mars is no longer just the next place humans will walk. It is becoming a hub where planetary and interstellar science converge. 3I-ATLAS showed that. One moment the orbiter was mapping terrain, the next it was scanning a visitor from another star. This adaptability hints at a future where space missions will not be siloed. They will be responsive, opportunistic, and collaborative. When our thoughts stretch forward, we sense another open question. If Mars can watch interstellar visitors, what else can it watch? Asteroids? Strange transients? Could Mars become a sentinel that warns Earth of unexpected arrivals? And if so, could this change how we defend our planet, explore our solar system, and read the messages carried by travellers from distant suns? Part 13. Advances in Comet Tail Physics 2025. When the missing tail of 3I-ATLAS became headline fuel, comet researchers quietly smiled. They knew tails were more complicated than most people realise. A comet's tail is driven by sunlight heating ice. That ice sublimates, releasing gas and dust. The solar wind pushes that material outward. Simple, right? Not exactly. Tail formation depends on particle size, composition, and geometry. In 2025, new research suggested that large dust grains do not form visible tails as easily as small ones. If a comet sheds mostly large particles, the sunlight cannot push them far enough to form a long visible plume. When scientists modelled these large-grain comets, they found that the tail could be so short it hides inside the coma. That means a comet could look tailless at first glance. Some researchers pointed to 3I-ATLAS as a candidate for such behaviour. If its dusty outgassing is dominated by larger grains, then its tail could be effectively invisible. That explanation is not proven, but it is plausible, and it is more mundane than alien sails. When another study suggested that certain volatiles, including carbon dioxide and carbon monoxide, can sublimate differently from water ice, the picture deepened. If 3I-ATLAS contains unusual ratios, its gas jets might be weaker or more directional. Strong jets could push dust backward, hiding the tail. Weak jets might not produce a tail at all. The absence of a tail does not guarantee technology. It might simply reflect a chemistry we have not catalogued well. When laboratory research explored dust fragmentation, scientists found that sublimation could break large grains into small ones mid-flight. That is relevant because a fragmented grain responds differently to sunlight. A comet could begin tailless and then form a tail later, or vice versa. The evolution could be erratic, confusing observers. If 3I-ATLAS shed most of its dust early, before observation, then by the time Mars saw it, the remaining grains might have been too large or too few. When a new model suggested that interstellar radiation history changes dust composition, researchers saw a connection. If 3I-ATLAS spent millions of years in harsh interstellar space, its outer layers might have been baked, compacted, or chemically altered. That production history could explain why its outgassing behaves poorly compared to typical solar system comets. The dust could be unusually cohesive, resisting fragmentation. Without fragmentation, the tail would not bloom. When we apply these findings, 3I-ATLAS becomes less of an oddball. It becomes part of a continuum of possible behaviours. It just happens to sit on the edge of known models. That is not cosmic heresy. It is an invitation to learn. The absence of a tail may not be a revelation. It might be a reminder that sample size matters. We have only seen a handful of interstellar visitors. Their diversity could be extreme. We may need to rewrite how we think about comet physics in the galactic context. When we imagine a subclass of low-tail comets, we see potential. Some may be shaped by unusual chemistry, others by history. Some might be primordial fragments, barely altered since their birth. Others might be processed ice that has travelled from star to star. Their physics might be more varied than textbooks suggest. And interstellar visitors give us a chance to test that range. When we connect this back to Mars-side imagery, we realise that tail physics does not require a high-resolution picture to be intriguing. Even grainy dots can tell us about coma brightness, shape, and motion. If 3I-ATLAS brightened in a way that suggests outgassing but never formed a tail, that alone gives scientists a puzzle. They can build models from brightness curves alone. When the conversation turns speculative, people wonder if the missing tail hints at exotic propulsion. But comet researchers caution against that. They remind us that anomaly does not mean agency. Many strange comets have confused us before. Most turned out to be mundane. The tail is not a litmus test for alien technology. It is, however, a meaningful data point that helps refine models. When the park closes, we hold on to this curiosity. If comet physics is evolving, what else will evolve? As we study visitors like 3I-ATLAS, we may update our understanding of how objects from other stars behave. And if our expectations shift, then perhaps the threshold for calling something artificial will rise. The next odd object might still surprise us, but we'll carry sharper tools into the puzzle. Part 14. Space Geopolitics and Data Sharing in the New Space Era. When China released its 3I-ATLAS images first, it felt like a narrative inversion. Usually NASA leads with stunning visuals and others follow, but here China moved quickly, publishing low-resolution dots and a short animation. NASA stayed silent, caught in the timing of a government shutdown. Europe followed with its own modest frames. the world found itself measuring not just the images, but the silence. When you look at the new, space era, politics rides shotgun, nations compete for prestige in science, data is a currency. China's fast release earned it a spotlight, even though the data was coarse. The United States, with its powerful high-rise camera, stayed quiet, and that vacuum filled with speculation. People wondered if NASA was hiding something. The real answer might be mundane. The agency was hamstrung by bureaucratic delays, but perception often beats reality. When we consider open science principles, we realize publicly funded missions are expected to share data. But timelines vary. Some missions release raw data immediately. Others impose months-long embargoes so researchers have first rights to publish. Those embargoes sometimes cause frustration. Scientists in different nations may hold data privately, while others wait. This dynamic fuels competitive tensions. When we recall Cassini data policies, or Apollo sample distribution, we see that data control has always been political. Who gets samples? Who publishes first? Who earns the citation? These questions matter. In the case of 3I-ATLAS, China seized the first release advantage. That changed the social narrative. It made NASA look slow, perhaps reluctant. But behind the curtain, there may have been nothing more than legal restrictions during a shutdown. When we imagine future contests, we see how data sharing might become an arena of soft power. If one nation controls the best imagery, it controls the story. And in a world where interstellar visitors draw global attention, controlling the story becomes influential. Imagine a scenario where an interstellar visitor shows something truly odd. The nation with the clearest data could choose when, how, and if to release that information. When the private sector enters the picture, the story complicates further. SpaceX, Blue Origin, and other companies may eventually host instruments that can capture data. Will private companies share openly? Or will they monetize data? What if the most dramatic images of an interstellar visitor end up locked behind a paywall? That scenario is unlikely today, but the new space economy encourages unusual arrangements. When geopolitical tensions rise, cooperation falters, joint missions struggle, shared data becomes rare. 3I-ATLAS arrived in a moment when the United States and China were not deeply collaborative. The event highlighted the cost of that separation. Multiple images existed across agencies, but no unified release occurred. That fragmentation invited conspiracy speculation. If a single international protocol existed, perhaps the data would have been synchronized and contextualized. When people talk about data wars, they imagine nations hoarding information for leverage. In space, that means control over orbital vantage, mission instruments, and scientific interpretation. The potential for conflict grows if visitors appear more frequently. If the Vera C. Rubin Observatory detects dozens of interstellar objects, data pipelines will be stressed. Who decides what is shared? Who decides what must be verified before publication? When we look ahead, an international framework could help. A treaty for interstellar visitor data release is unlikely soon, but conversations have begun informally. Scientists advocate for transparency. They warn that secrecy breeds suspicion. They push for public repositories, open pipelines, and unified messaging. But governments think in strategic terms. Sharing data means sharing power. When we close this part, we recognize that 3I-ATLAS is not just a puzzle of chemistry and trajectory. It is a story about how nations communicate, withhold, and shape narratives. And if the next visitor looks stranger than this one, the politics may grow louder than the science. That uncertainty leads us to the next question. What missions, instruments, and approaches will help us meet the visitors of tomorrow? Part 15. What's next? Missions, instruments, and what to watch. When we step back from 3I-ATLAS, a question lingers. What now? The answer is both thrilling and uncertain. The world waits for NASA's high-rise imagery. If those pictures appear, they may confirm or refute current guesses about tail absence. They might reveal subtle jets. They might show nothing unusual at all. But their release could shift the conversation dramatically. People will compare them to China's dots, looking for discrepancies, surprises, or validation. When peer review studies appear, they will wrestle with the object's composition, brightness curve, and non-tail behavior. Some will favor exotic chemistry. Others will back geometry explanations. A few may reach for more speculative hypotheses. The debates will be measured in archive preprints and quiet conference rooms. The world of comet physics may adjust. A subclass could be named. The mystery of low-tail interstellar comets might become mainstream. When we look toward missions, the European Space Agency's Comet Interceptor stands out. Designed to wait in space for a never-before-seen comet, it could reposition to study a visitor up close. If another 3I-ATLAS type object appears, Comet Interceptor might be our best chance to inspect it directly. China's Mars sample return mission, still in planning, could host instruments useful for external observations. The idea of piggyback capabilities is gaining traction. If you already have a spacecraft in orbit, why not give it outward-facing tools? When we imagine what viewers should monitor, the checklist grows. Watch for data releases, scan preprint servers, follow mission press releases. Public engagement matters. If Mars becomes a standby observatory, we may see more rapid releases. People could track raw images from Tianwen or MRO in real time. Imagine a dashboard showing active observations of incoming objects. The boundaries of citizen science could expand. When we speculate, possibilities bloom. 3I-ATLAS could reveal jets at the last minute. It could fragment, shedding pieces that drift like faint embers. Another interstellar visitor might arrive sooner than expected, perhaps one with a visible tail, or an object showing odd acceleration. If Mars builds a network of instruments, it could act as an early warning system. That would change how we respond to cosmic arrivals. When we consider the biggest unknown, we realize that our understanding of interstellar visitors is embryonic. 3 objects do not define a category. The next 10 could change everything. Maybe some will be huge. Maybe some will be metallic. Maybe one will carry unusual radio signatures. None of this is guaranteed. But the possibility fuels imagination. When we end this story, I want to leave you with a thought. The universe sent us a visitor that behaves strangely. We caught blurry glimpses from Mars. We argued about missing data. We speculated. We waited. And now we stand at the edge of a new chapter. The next visitor could rewrite our cosmic story. It could force us to rethink how we observe, how we share, and how we prepare. When you look up, remember this. The unknown does not wait for us to be ready. It arrives when it chooses. Our job is to pay attention, ask careful questions, and keep our minds open. The cosmos is not quiet. It sends messages. And sometimes those messages look like dots drifting through the dark, daring us to understand.